All right. Well, welcome, everybody. Thanks for attending today's webinar, How Do Humans Use Hot Water? We're going to discuss the way that humans use hot water by first looking at smart faucet behavioral study. Next, we're going to look at a couple presentations that explore the importance of accurate draw profiles, which help us understand water usage patterns in buildings. My name is Chris Perry, and I will be your moderator today. So most of you have probably heard these at this point, but I'm going to read through some housekeeping announcements before we go ahead and get started. So your screen is customizable. Feel free to make various windows as large or small as you want. You can minimize them to drop to the menu at the bottom of your screen. Click through the widgets at the bottom of the screen to be sure you can see all the options. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode, but you can use our Q&A box at any time during the webcast to ask questions. I will then give them to the presenters, and they can respond at the end of their presentations. And if you can't see the Q&A box, it should be available at the bottom of your panel there. Presentations will be available for on-demand viewing within a few days of the Engagement Hub, through the Engagement Hub. And at the end of the session, we'll be opening chat rooms on the Zoom platform for anybody who wants to continue talking about these topics. So to access the chat room, there's a chat room icon in your menu bar with the link. And on behalf of ACEEE, we want to first recognize and thank our sponsors for the event. Our platinum sponsors are Rheem and A.O. Smith. We thank them very much for their support. And our silver sponsors, Bradford White, Green Power EMC, Jackson EMC, NEA, which is the Northwest Energy Efficiency Alliance, and SoCal Gas. And we thank them all for their support. And so I am going to introduce our distinguished panel of speakers. First speaker is Aaron McDonald, Assistant Professor of Mechanical Engineering and Faculty Director of the Master Design Impact Program at Stanford University. Our second speaker is Peter Grant, Senior Research Manager at Beyond Efficiency. And our third pair of speakers are Travis Ashley, who's a computer scientist, and Walter Hunt, a Senior Research Engineer at Pacific Northwest National Lab, or PNNL. And so our first speaker, Erin McDonald, is her research at Stanford combines psychology, economics, and marketing into engineering design methods to better represent the user. Erin is going to discuss findings from a behavioral research study on smart faucets, which is in air quotes, and you'll see why very shortly why that is. And so we're actually going to start with a short video here, assuming that it works properly. So give it a second to load, and we'll start the video up.
At the heart of a lot of the work we do in this lab is to acknowledge that people are kind of neglected by engineers. So if you asked an engineer to design a sink, they would focus on the sink, right? On maybe making the handles ergonomic or the temperature feels just perfect. But they might not think, hey, let's design the person's habits.
Water is a big issue today in our society, especially here in California. We're constantly worried about the drought. Another thing is that people aren't always aware of their water usage, and finally, the faucet itself just hasn't been innovated in a very, very long time.
We sought to see if this smart faucet could encourage people to save water while using it. And we also wanted to see if people's habits were adjustable. If interacting with this faucet could then change how people interact with a manual faucet.
We're not trying to say everybody uses the sink exactly the same way, which is what existing automatic faucets do. What we're trying to do is meet people where they want to be in their preferences for washing their hands and doing dishes by adapting to how they use the sink with a super smart sensor and machine learning algorithm that would learn their habits and adapt to them over time. Now, this experiment doesn't do all of that, because before you invest in the sensors and refining the algorithm, the good thing to do is check when people like it, would they save water. It's called a Wizard of Oz experiment because we have the sink, but then we have a camera instead of sensors, and we have the camera feeding to a computer behind a wall. The student is controlling the sink, and the participant can control the sink. So they both have control of the sink. And in that way, they think that there's a sensor helping them wash their dishes, but actually it's William.
I had been watching them throughout the first phase to kind of understand their preferences and kind of how they like things. And using that information, I'm trying to leverage their cognitive style or their user behavior style to see if I can help them use less water while still keeping them happy. And we kind of measure happiness by if they are still manually adjusting the faucet.
Using this approach, we got 26% water reduction. But then there was a third step of the experiment, which was to wash your dishes again, but with no smart algorithm. And what's super cool is that people retain the training on using less water, and versus their first wash, they use 10% less water. Imagine a house where it's not just your faucet that does this, but it's also your shower, and every faucet in the house knows every person. I think once you get people interested and excited in conserving water, that there's a lot of possibilities.
For more, please visit us at stanford.edu.
Great. And with that, I'm going to turn this over to Erin to talk more about the findings from this research study.
Thanks a lot. So yeah, some of these slides just say the same thing that the video said, but I especially want to acknowledge William and Sam, two of my graduate students who were featured in that video and did such a great job explaining everything. So we like to think of this design as better than smart, telepathic. And what you saw in the video should be extended with sensors to understand who's coming to the sink, what they're bringing with them. For example, is it a plate? Is it a vase they want to fill with water? So that the sink has some understanding of the function that it's about to perform, just like William did in the video. And that's not beyond reach. It would be a big leap forward in water technology in the home, but you could also imagine, for example, your preferences following you when you go to a hotel or to someone else's house or from work to home. And now I also want to mention with things shifting actually to making sure people use a lot of water when they wash their hands to do it very efficiently, these sensors could also encourage that behavior. And for example, make sure that the water is hot enough and is on for a long enough duration if they see somebody approaching to wash their hands, for example. So some of the motivation for this project comes from the fact that a lot of water used in the home doesn't yet have any water-saving technology associated with it. So faucets, as far as water conservation, have aerators in them, and that technology is quite old, and maybe a little bit of flow control. But in terms of thinking, how do we decrease people's water uses at the faucet, there haven't been many advances in homes. So let's skip this. I think that the video covered that very well. So a couple things here. Over the time, as the faucet gets to know you better and better, it would perform better. So it would be an algorithm that has a bonus or a penalty for when the user touches the faucet to adjust it. And in that way, it would learn your habits more and more. So you would have to touch the faucet less and less. So this is interesting. These are just some of the details of how the faucet worked. There was a servo motor in each of the handles, and that servo motor could be controlled by computer, or it could take in the input of the user. And that's how you get that two-way communication. The computer is sending signals of how to turn on the water, and also the user is providing feedback. Well, no, I didn't want that much, or I wanted more. And the actual experiment in the lab involved washing a set of dishes with cornstarch, a sticky green cornstarch paste all over them. And all the participants did it 3 times. If they were in the experimental study, they washed with William controlling it in the middle. And then the bookends were their own washing. And if they were in the control, they just washed the dishes 3 times. These are details on the experimental procedure. I basically just said what is on this slide. So skip that one. Okay, let's look at some results. So when you were in the control condition, they actually used more water over time compared to the first phase. In the second phase, when they washed dishes by themselves, and then in the third phase, when they washed dishes by themselves. Whereas when they were in the SMART condition, or the telepathic condition, they washed dishes, they saved 27% water when William was driving, and then they saved 10% when they were quote unquote driving again. But they learned that they could do the same task with less water. So what we don't have is an indication that over time they would retain this training. But the hope is that even if you could install this faucet in one portion of their lives, for example, a work faucet but not a home faucet, or a home faucet but not a work faucet, that they would learn to use less water to do the same tasks over time. These are some details on how often people touched the handles. You can see in the second phase, for the SMART group, which is the middle left graph there, that the participants were really only touching the faucet at the very beginning of the study. Whereas in the control group, the patterns in all 3 phases look very similar. So William was doing a pretty good job of being a computer and understanding what people wanted, because they didn't spend a lot of time adjusting the faucet when he was driving. What might be counterintuitive is that there was little correlation between how much time people spent washing the dishes and how much water they used. And one thing that we found that we really need to explore in the future is that people have very little knowledge of how much water they use washing dishes. People that were using up to 14 gallons, which involved emptying the bucket under the sink where we were collecting and weighing the water to reuse it in between phases, were reporting that they were using as little as like 1 gallon of water to wash the dishes. So there is a chance that increasing people's knowledge of how much water they're using may lead to behavior change. But what this experiment shows is that just changing their behavior and showing how they could behave differently leads to behavior change, which I think is a more direct route than hoping that knowledge will change behavior. Yeah, so as I said, everybody underestimated the amount of water they used, but some people used up to more than 14 gallons because the bucket held 14 gallons and we had to change it. So just to wrap up here, conclusions. The experiment showed a positive interaction with the autonomous telepathic faucet and potential for reduced water use. Additional findings suggest that the faucet could train people to use less water, and that this Wizard of Oz experiment, where William was a wizard, was useful in understanding the effectiveness of how an algorithm could be implemented before going through the labor of training sensors and building an algorithm. And that's a brief summary of this work. Thank you.
Great. Thanks so much, Erin. I think we'll probably save Q&A until the end, unless, let's see if this is a clarification question. I think you did really well on time. Let's ask a couple now, and then we can maybe touch on more later. So Jessica Atwater from Clear Result says, telepathic faucet, very cool. Did the research include how the dishwasher's water usage affected how the water heater was cycling/reheating?
So it was an inline water heater. And so it provided a continuous stream of water at a continuous temperature as people turned it off and on. This brings up a very interesting point, which was that the inline water heater isn't instant for the first person in the experiment, right? It takes a little bit of time. And so we got into this situation where people didn't know if the faucet wasn't working or if it was taking time to heat up. And that's something to think about when you go to a full smart faucet. there'll be a moment of hesitation until people get used to the system where they don't know if the faucet has served them the wrong temperature or if the instant water heater is just taking a second to heat up, if this exact implementation was used.
Great, thanks. That's great. Jessica says thank you. And we have one more. Gary Klein asks, a very large percentage of faucet draws are too short/small to reach the faucet as hot water. Any thoughts about how this concept could adapt to this?
Yeah, I think probably for very short faucet draws, maybe this concept will operate in a very simple mode, because I think it'll take a second for the sink to understand what's happening, unless it comes with a pot or a vase and it's a fill task. Hands, you could do maybe you have something on your fingers and it goes real quick. The faucet will have to guess what mode to be in. So there'll likely be a default mode with like a neutral temperature that it would learn to start in. And so that likely, just because of the way faucets work, unless you have a completely recirculating system, wouldn't be that warm for the first few seconds.
Great, thanks so much. So I think it makes sense to move on. But thanks again, Erin. Really great presentation.
Those are good questions.
Yeah, I'm sure there will likely be more after. Hopefully we can get to them all. So our next speaker is Peter Grant. He's a researcher at Beyond Efficiency, and his research ranges from AI building control systems to automated processes to improving the accuracy of simulation models. So in this presentation, Peter is going to take a look at California's Title 24 draw profiles and also talk about a draw profile tool that can help evaluate policies like building codes and appliance standards, as well as technologies like drain water heat recovery or heat pump water heating, load shifting. And so with that, I'm going to turn it over to you, Peter.
All right. Well, good morning and or afternoon, everybody. And as Chris said, I'm going to be talking a little bit about basically what could now be treated as a source of hot water use data. Basically, Title 24, for those of you who are familiar with it, or I'm sorry, for those of you who are not familiar with it, is California's building energy code. And we use a simulation model to predict how well the building will perform. And part of doing that is estimating how much energy the water heating system uses, which means you have to have some reasonable approximations of how people use hot water. So I'll be telling you about that, a little bit about how it got constructed, a fair amount about what's in there, and a lot about how we've created tools that you can use to mine this data for your purposes. So here's an outline of what I'll be talking about today. The first is background, what are these Title 24 draw profiles? Why did they become necessary? Then move into more of a description of what they are, some of the details behind them, and move into the draw profile creation. Or if you start with this Title 24 based data set, how can you create a useful draw profile from it? And then I'll move into Beyond Efficiency's draw profile tools, the computer scripts we have that you can use to create the draw profile that you need. And then I'll talk about some of the strengths and weaknesses, right? The Title 24 draw profiles are very appropriate for some situations, but not others. And so we'll dive into some thoughts there. And then a little bit about possible uses or things you might want to use these draw profiles for. So starting with the background, California was adding heat pump water heaters to Title 24, which means we needed our code compliance software, CVEC-RES, to be able to simulate the performance of heat pump water heaters. And the draw profiles that were currently in CVEC-RES when this project was started were not adequate. Heat pump water heaters choose between using the heat pump or the electric resistance elements. They do it very rapidly. And this means you need to run simulations with very low time steps. The model is based on Ecotop's heat pump water heater sim, and they strongly recommend 1-minute time steps. Now, at the time, CVEC-RES's draw profiles were hourly averages. So you can imagine that using a 1-minute time step simulation with hourly average data, well, there's no point in using a 1-minute time step simulation if your input data has an hourly average. So they needed better draw profiles in order to make the heat pump water heater simulation model work. So they reached out to the consultants in California, and those consultants created new draw profiles. I'll tell you a bit about what's in them, but if you want a lot more detail, you should really either ask Jim Lutz or look at the presentation he gave at the Hot Water Forum back in 2017, which is listed on this slide. There's a lot of really good information there. But so the really high-level bullet points are that the consulting team took data from Aquacraft's study, and Aquacraft monitored hot water use in thousands of houses in California. And so this created basically a treasure trove of data that they could use to mine and create daily draw profiles. So they broke out, midnight to midnight daily draw profiles from all of this data set. And then they did a lot of data analysis and created algorithms to combine these different daily draw profiles into a 365-day annual draw profile. And so keep in mind, these are not annual draw profiles from a single building. It could be one day from house 1, another day from house 2, another day from house 3. They kind of get combined. And one quirk of the code compliance situation is that CBEC is assuming that a house will last for 50 years or more. The average set of occupants will not live in the same house for 50 years or more, so they had to assume there will be different occupants in the house from day one to the end. And they did this by using what's called the RAS data set from the KEMA study back in 2010. And this study shows the percentage of houses with a certain number of bedrooms that have different numbers of occupants. So it'll say things like a 3-bedroom house, 40% of the time will have 1 occupant, 50% of the time will have 2 occupants, 9% of the time will have 3 occupants, and so on. I made those numbers up, but I hope they highlight the situation. So here's another way of thinking about a description of the Title 24 draw profiles. They created a bunch of different daily draw profiles. These daily draw profiles represent between 1 and 5 plus occupants. So they don't go to 6, 7, 8, it's just 5 or more. And then they represent weekends, weekdays, or holidays. And then they combine these different draw profiles by just putting 365 of them sequentially, and that way create an annual draw profile. And the number of occupants in any different daily draw profile changes throughout the year, trying to capture that variation in number of occupants over 50 years. So then these draw profiles do represent mixed water flow, not hot water flow, and they do not include distribution system impacts. So there have to be some additional calculations beyond the original data set to both identify the hot water flow and to take into account the distribution system impacts. So if you get the actual data set for the Title 24 draw profiles, this is what it looks like. You get a big text file, and it's split into 2 sections. One is describing daily profiles, and the other is describing annual profiles. And I've got an example of each here on the slide. If you look at the daily profiles section, the second line says DHW day use, and then in quotes, 1D0. And so this is a single daily profile called 1D0, meaning with the 1 representing 1 occupant, D representing weekday, and then 0 just representing variant 0. There are like 10 of these single occupant weekday draw profiles. And then you can see following that, there are all these little events labeled FAUC, meaning it's a faucet draw, and then it's got the details for the draw in parentheses, so you can figure out the details of each specific draw. Then if you move over to the right side, you see that's where it's looking at annual profiles. And the top line says define DHW 1BR. So this is looking at an annual draw profile. 1BR stands for 1 bedroom, so it's a 1-bedroom dwelling. And then the next line has the choose 1 day of year, and then the first thing in quotes is 1H8. So that means the first daily draw profile in this annual draw profile is 1 occupant, H is for holiday, and it's number 8. So January 1st, 1H8. And then January 2nd, the next entry is 1D4. And so you could envision digging through these text documents to collect all the details and for each daily draw profile and assembling your annual draw profile accordingly. And that's kind of what you have to do, either do it by hand or write a program to do it for you, but you have to assemble them that way. So if we look at the Title 24 draw profiles and just think about what's in the data set, or I'm sorry, what isn't in the data set, we notice the things we have to do to convert this data into a useful draw profile. First, there is not a hot water draw profile. It's a mixed water draw profile. We can overcome that with calculations if we know the inlet water temperature, which also is not directly in the data set, but is available. And then also it doesn't have the distribution system losses. So we need to go through those 3 different steps to convert this base data set into a useful draw profile. So how do we do that? First, how do we create a full annual draw profile? First, we identify the annual mixed water profile, and that comes out of the data set, right? Here's that same example from a few slides ago where it's just DHW1BR, and here is the list of the different daily draw profiles that you combine to create the annual draw profile. So then the next step is to copy paste the daily mixed water profiles in that order, and we can create our annual mixed water draw profile. And so here, this is that same example from the previous slide. We're just taking that and putting it in to our annual draw profile as needed. I guess I could have improved the slide by making that 1H8 because that was the first day in the annual draw profile, but I'm sure you get the concept. And so then third, you have to calculate the inlet water temperature for this building. And this equation is the one that's used in Title 24. So it's designed for Title 24. And you just calculate the inlet temperature based on the ground temperature and the average outdoor temperature over the last 31 days. And I want to point out that other equations can be used as needed. So if you have a inlet water temperature algorithm that you think matches your case better, that can be done. And then fourth, you calculate the hot water draw profile. You do this by doing an energy balance. You've got your mixed temperature, you've got your calculated inlet temperature. T set can be the set temperature of the water heater. And then you've got your inlet temperature again, and you just do an energy balance at the fixture to figure out what the hot water flow rate has to be. And finally, you can calculate the distribution system impacts. And by distribution system impacts, I mean, this is the hot water that gets trapped in the pipes after a hot water draw. And so in Title 24, we have these equations that estimate how much you have to increase the hot water consumption based on how much is trapped in the pipes afterwards. These equations are, they're pretty specific to Title 24. And again, just like the inlet water temperature calculations, if you have a better estimate for your particular project, you can use that. It's just the same calculations. And so that's how the Title 24 draw profiles are created. And Beyond Efficiency actually has draw profile tools that can do this automatically. We've written Python scripts that generate the specified Title 24 draw profiles. They can be used to create draw profiles for single and multifamily buildings. And this is especially interesting if you have a multifamily building where you may have hundreds of apartments. You've got your choice. You can combine all of the draw profiles into a single draw profile for the building and print it out in a single file, or you can create one file for each dwelling, just depending on how you want to look at it. And then the output of these draw profile tools is a CSV file. And the file name describes the simulated building. So here's an example of the inputs. I just copy and pasted text straight out of the Python tools. And you can see that we have these descriptive variable names. For example, the first one is building type. You can enter single if you want a single family building, multi if you want a multifamily building. SDLM is referring to the standard distribution loss multiplier, which is used for estimating the amount of hot water trapped in the pipes after the draw. And it says yes, basically saying we want to take that into account. You've got the water variable, which is set to hot, basically saying we want this to be a hot water draw profile instead of a mixed water draw profile. And we've got a bunch of different variables here, describing these same things. I won't go into the details. I'm sure you can figure them out if you want to. But you can see, it's user-friendly. You just enter the variables describing your building, and then we can create a draw profile accordingly. And so when you've got it set up, you push the run button to run the program, and here are the outputs you get. The top output is a file name where you can see that all of the variables that are used to specify the building are written right in the file name. It says building equals single, so it's a single family building. CZ stands for climate zone equals 1, so it's in California climate zone 1. You've got the water set to hot, the profile states the number of bedrooms, and so on and so forth. So this way you can easily see, just looking at the file name, what it is you're looking at. You don't have to open it up to figure out what draw profiles are contained in that draw profile. Or, I'm sorry, what buildings are in that draw profile. And then if you do open it up, you've got these different columns basically providing all of the details of the different draws. So the first column is the day, just what is the code of that day. And then the day of year, we've got one here, so it's all January 1st. And then it shows things like the duration of the draw, what fixture it goes to, what is the mixed water flow rate, the calculated inlet water temperature, and so on and so forth. So all the information needs right there, and it's pretty straightforward. And it creates a pretty usable draw profile. So let's talk about some of the strengths and weaknesses. Of course, these are highly flexible, right? You can create a draw profile for any building you want, any number of bedrooms, single, multi, whatever you want, so long as it's in California. That's a current weakness, right? We've got the SDLM and the inlet water temperature calculations for California. But these tools can be adapted. You would just need to add different weather data, different inlet temperature algorithms, etc. So if you have those handy, we could make use of them. One of the real strengths is that this is real data. People actually use hot water in this way. It's not a simulation assumption. And then, of course, with the weakness that came from just the way the data set mapped to the assumptions needed for code compliance is that it does assume different occupancy. So you don't have the same occupants every day. You have different numbers of occupants depending on the day. And it fits very well for code compliance, but maybe you need to do a simulation over a year with 2 occupants. And we could build a different annual profile using the data set, but that would take some work. So strengths and weaknesses there. And then just some thoughts on how these draw profiles could be used. I know I do a lot of work on case analyses. For those who don't know, CASE stands for Codes and Standards Enhancement. It's how we update Title 24. And you need to estimate the cost effectiveness of technologies, which means you need to know how much hot water people are using. We've got the data set. Laboratory experiments. You want to be able to run your test in somewhat realistic situations. Now we've got a data set. Same with other simulation models. You want to run your simulation in realistic situations. Now we've got a data set. I'm sure there are other uses, and I'd love to hear what you think. And I have to apologize, Chris. I'm pretty sure I went long. So here's my contact information, and we're ready to move on.
All good. We're doing well on time. Thanks, Peter. We do have a question for you real quick before I forget it, though. I'm got a question from Jonah Shine at EPA asking if there is a link to Aaron's video, and I just wanted to send it out to everybody because I figured, if you want to see it, it is hosted on YouTube. So I figured Jonah might not be the only one with that question. Okay, so Peter, I have a question for you that came in during an earlier part of your presentation from Gary Klein. So why are there no days with 0 occupants, no vacations allowed?
I haven't really looked into that very much. There are certainly low use days. I don't know if there are any 0 use days. Gary, I'd say the 2 of us should set up a phone call with Jim.
All right. I'm sure you can talk about that more in the Zoom chat afterwards. And then I think if we have time at the end, we'll address more Q&A, but for the sake of time, let's move on at this point. So thanks very much, Peter. That was great. We're going to move on to our final presentation here. Move to the right side. Okay, great. So our final presentation, we're going to hear from Travis Ashley and Walter Hunt from Pacific Northwest National Laboratory, or PNNL. Travis and Walter will share results from a PNNL draw profile study. So might be some overlap with the previous presentation. And so their study allows them to identify small, medium, and large draw profiles. And like we've talked about, these draw profiles can be used to evaluate innovative hot water technologies or policies. So with that, I'm going to turn this over to Travis and Walter.
All right, thanks, Chris. Hello, everyone. Thanks for joining our session today. As Peter mentioned in the last presentation, draw profiles are very important in hot water research. At PNNL, we have a team of folks who do technology evaluations. Travis and I are part of that team. Commonly, we're looking at water heating technologies. And when we're looking at water heating technology, you have to impose some type of draw profile on the system in order to evaluate its performance, or to look at impacts on the home in other regards. There's many different available resources in the industry that you can look at an individual draw profile and impose that on a water heating system. But at PNNL, we had a data set that we also wanted to explore this issue of draw profiles. So in looking at our evaluations of technologies, we wanted to impose draw profiles that are field representative, and also profiles that are adequately stressing a given water heating technology, as it would see in an actual field environment. So there's two things that are kind of unique about this analysis that we did that we'll share with you. One is that we're looking at CTA 2045 data. So we'll talk about some of the details of that, but it's some power and energy data. So we were not actually measuring hot water draws in the field data collection. And the second unique thing is kind of the approach that we took. So previous work in draw profiles and an analysis of it has generally looked at some field data set and then created or formed draw profiles based on that field data. So we kind of took a different perspective, and we sought to identify a single day at a single site, which was representative of the overall data set. So with that, I'll hand it over to Travis, who will talk a little bit more about our field data set.
Thank you. So there were a total of 98 field sites. We had electric resistance water heaters in the study, and they're all located in the Pacific Northwest. Data collection was at 1 year for 1 minute intervals using the CTA 2045 modules. And this data included power consumption and present energy. And present energy, if you don't know, it's a CTA 2045 value that captures the amount of energy a device can receive. So for water heaters, this is basically an indicator for how much energy is needed to heat the stored water to the tank's set point. So CTA 2045, it's a method to control water heaters. However, for this particular study, we only use it for collecting data. So there's no CTA 2045 shed commands issued in this study. So we analyzed field data in order to identify representative draw profiles, and we used 5 analytic metrics listed down here at the bottom of the slide. There was the daily energy consumption, and then to help characterize the hot water distribution, we examined the hours of significant draw. And so this is the number of hours the power consumption exceeds the 700 watt hour energy. And this number we determined during the analysis of the data. And then to help characterize the profile shape, the last 3 metrics we used, they are for the AM and PM peaks. And the peaks we defined in 3-hour windows in order to capture the cluster of power draw around the actual peak hour. And so we don't have time to walk through the entire analysis, but there will be a slide. It contains more details of the steps. But I do want to highlight 2 analytic perspectives in this next couple slides. So this is a histogram showing the median daily energy consumption for each of the 98 field sites. We use this plot to define the targeted daily energy consumption for the small, medium, and large representative drop profiles. So for instance, the medium profile daily consumption target was set to this 50th percentile down at the bottom. And this was at 9.1 kilowatt hour energies. And we used assumptions for energy efficiency and the groundwater temperature, and estimated that the daily hot water draw for this medium profile would be 49 gallons of hot water. And then this is another perspective we use in our analysis. This it shows the daily energy consumption versus the number of hours of significant draw, both using the median values for the 98 field sites. So the key takeaway from this plot is that as the daily consumption increases, so does the number of hours of the significant draw. And this perspective helps with the analysis by identifying the frequency or the distribution of hot water draw. And so I'll turn the rest of the presentation over to my colleague, Walt.
So let's see. All right, so here it kind of gives you a snapshot of 3 of the draw profiles that we identified. So these 3 different tables here, we just arbitrarily selected small, medium, and large for the 25th, 50th, and 75th percentile. So it gives us, a range of usage across our data set. And then you'll see our 5 analytical measures there atop in the columns, a section of those tables. The daily consumption, hours with a significant draw, difference between AM and PM peaks, and then the 2 ratio metrics as well that help kind of shape the profile. So you can see how those different small, medium, large profiles kind of took shape in our analysis. And we were, again, looking to identify a single day of those roughly 5,000 days of data that we had, which kind of best represented its target area. So the selected day row that you see there, that's an actual given site of a given day's profile. And then we tried to find something that was very close to what the median was for that group and that subset. So looking through there, you can kind of see some of the different metrics that we're showing. Again, Travis just mentioned that as consumption increased, we were seeing that number of significant draw hours increased as well. So you can see that across the 3 groupings. The time difference between the AM and PM peak was 10 or 11 hours there. And then you can kind of see those 2 shaping metrics, the ratios of the peaks and the peak to the consumption. So you can see that for most of the 3 profiles, the peaks were fairly balanced, both significant AM and PM peaks. And then the 2 peak periods, again, we were looking at a 3-hour window for a peak period. So those took up a substantial portion of the overall daily usage. So that kind of gives you a summary of those 3 groupings with numbers. And then here you can see the actual 3 days that were selected based on this. And so this is the actual power consumption data, hourly averaged here for those 3 days that we identified. And again, these are days that we've done through analysis that are representative of the overall data set for those 3 target categories of small, medium, and large. So here you can also see the prominent AM and PM peaks across the groupings. Another thing that jumps out to me is just the randomness that you see. And of course, in the field, in practice, hot water usage is random. And these are real sites, real customers that created these profiles. And so that kind of as well is a great thing, is looking to use these curves and plots to evaluate water heaters and look at the actual stresses that water heaters would see in the field. And so you could use these strategies and these profiles for a number of different things. You could look at them for the power consumption data. So that is the data that we were working with here, was power consumption, and maybe load shifting or storage would be of interest to some researchers. And so you could look at these as representative, single days for that type of research. But one of the initial research uses that we had was trying to look at draw profiles and using those draw profiles to then evaluate water heating technologies. And so we were able to come up with a little bit of a method. And again, we have a summary slide that talks through that method in greater detail about how you could take some of the CTA data and estimate what the draw profile that would be that then created this power consumption. So in the CTA data, these are two of the values that you can receive from that pathway. Current watts, which is the power consumption of the water heater. So that's the orange plot there that references the left-hand side axis. And so electric resistance water heater, so it's operating at 4,500 watts when it was on. And then the present energy metric, which is the green plot on the right-hand axis. And so that is the amount of energy that a device can receive. And so from a water heater's perspective, as the present energy variable goes up, it's either standby losses or losses are occurring within the system, or a draw is occurring, hot water is being removed from the system. So the resolution of that in the CTA platform is around a half a gallon. So if you see a half a gallon loss or removed from the system, then that will register an increment up in that present energy metric. And so when the present energy metric is at 0, that means the water heater is fully charged. And then as it begins to pick up, it would either be due to a loss or hot water draw. And so the present energy metric gives you an indication of when draws are occurring. And so if you're able to kind of take out and filter out some of those losses, you have a pretty good map on when draws are occurring throughout the day. CTA data is minute-based, so it gives you really good granularity on when draws are occurring. But using that present energy data is very tricky on trying to translate that to hot water usage or gallons consumed. But with low resistance water heaters, you can make a fairly good approximation with using the power. So kind of by using those two variables in tandem, you can provide a little bit of a estimation on hot water usage throughout the day. As you'll see there kind of in the plot, as hot water is being used, as the present energy variable is going up, then you'll see that threshold where now the water heater kicks on, and by looking at its runtime, its amount of power consumed, you can then make the approximation for hot water consumed. So that's what we did for the medium target day, and you'll see a plot of that here on the screen on the orange plot. So that's translating that CTA data, the power data, and present energy data into gallons consumed of hot water. And again, you can do that by filtering out losses and making assumptions for water heating efficiency, groundwater temperature, and set point. We have on the plot here a comparison of this medium case to another industry profile that's been established just for an individual site, individual water heater usage. So you can see the two align fairly well, but you'll notice that we do have a more significant draw that was shown here on the day that we identified in comparison to other industry profiles. And so in the world of technology evaluations and water heating evaluations, imposing different draw profiles, stressing that water heater under different scenarios, seeing what its performance is under those different scenarios is, of course, immensely important as we look to develop and deploy technologies into the field. So we don't have the results to share today, but we're currently right now have an advanced water heating technology at the PNNL lab homes that we're stressing under some of these different profiles. We're using available industry profiles that are already published and out there in the literature, as well as we're using some of these profiles that we've identified and established from some of our data that we've collected. And so that will allow us to look at technologies and evaluate their performance from a field perspective.
All right. Walt and Travis, thank you very much. Great presentation. So we had a question come in from Jessica Atwater at ClearResult. Said, were you looking at peak hour for grid usage or the water heater's peak hour?
Is the water heat. So one of our metrics was looking at the AM and PM peaks and just the daily peaks in general, and so that was the water heater's perspective.
Okay, great. So we have some time here at the end for Q&A. So if you have any questions, send them in. We have a handful that I'm gonna read now. So we're gonna go back to Erin for a question that she received shortly after her presentation. So Stephen Buchenberger from University of Cincinnati asked, what fraction of residential hot water use occurs at the faucet taps as compared to clothes washer and dishwasher? Hey, Erin, I don't, if you're talking, I think you're on mute.
I'm sorry, my connection just dropped for a second. What was the question?
Sure. All right. So Stephen Buchenberger from University of Cincinnati asked, what fraction of residential hot water use occurs at the faucet taps as compared to clothes washer and dishwasher?
Yeah. So would it be all right if I move the slides? Because I have that on a slide.
Yeah,
but
sure.
It's back quite a bit. Okay.
And we can select, I think I know what slide you're talking about here. I just pushed it to the audience. Is that?
Okay, thank you. Yeah. So if you look at this slide, which is not showing for me, I don't know why. In the audience?
Yeah, how about now?
Still can't see it, but oh, there it is. Right, so this was a report. It's a little old, it's 2011. You can see the reference at the bottom if you want to look at it more carefully. It's from the California Single Family Water Use Efficiency Study. And it looks like the washer is using 18%, and the dishwasher is using less than 3%. Dishwasher and oiler is less than 3%. So that could be some overall look at that.
Great, thanks. And for our other presenters, if you're not speaking, can you please mute? There's a little bit of feedback. All right. So there was one question that we got. So I'm not. This wasn't addressed to anybody. I think it might be for Erin, but I think Peter, Travis, Walt, you all could address this too. It's more of like a health perspective question. So this is from Alex Friedland from GTI. He says CDC guidelines say that warm water does not benefit microbe removal. Is there merit in using technologies that discourage the draw of hot water for hand washing?
I think you'd have to be fully on board with the first part of that statement, which I'm not sure that I am, because I certainly know that we are in the human session, right? And so while using hot water might not promote the removal of microbes. It promotes the keeping the hands under the faucet for a longer period of time. So you would definitely want some hot water in the mix. You know, I remember living places with cold water in the winter and hot water, my hands weren't under that faucet. So there's two elements to it, I would say.
Yeah, I'm trying to dig through my notes from last week to figure out which specific presentation I'm trying to reference. But there was one presentation that was really talking about Legionella growth in distribution systems. And unfortunately, I can't find my notes quite yet. But the general takeaway was that Legionella grows really well between 80 degrees Fahrenheit and 110 degrees Fahrenheit. So, you know, that's very much backing up your comment, Alex, that I'm trying to find it right. Warm water does not benefit microbe removal. I'd say it's worse than that. Warm water encourages microbe growth. So is there merit in using technologies to discourage the draw of hot water for hand washing? I don't think I can take a stance on that. I think it's a very interesting question. I'll put it that way.
All right, that's fair. Thanks for filling that one. So we had another, and actually, Peter, while you're on, so Devin Calder asked, and I think you already responded, but I thought it might be good to share with everybody. Devin asked from the Atmospheric Fund, asked, "Hi Peter, thanks for the great presentation and sharing the cool tool. What would next steps be to make this tool work for our work in Toronto, Ontario, Canada?" And I think that question probably applies more broadly, like where can we use this beyond, California?
Right. Yeah. Yeah. So that was a great question, and I did answer Devin directly on that one. But so if we wanted to talk more generally instead of specifically on his Toronto application, I would say that there are a few ways we could try to make the tool more appropriate for your specific application if you want to use it. The first one, and definitely like mandatory, is that this tool currently uses weather files for California. And if you want to create a draw profile for somewhere like Toronto, California weather is going to be pretty darn inappropriate. So we need a local weather file. Fortunately, a lot of weather files are available, so that's a hurdle we should be able to overcome, but that's pretty much mandatory. Then we would also want to look at potentially some of the assumptions that are used in creating the Title 24 draw profiles and how you want to respond to those assumptions. For instance, I talked about the standard distribution loss multiplier and how that is a way to estimate the amount of hot water that's trapped in pipes. That was based on data in Californian houses. Maybe you have more accurate, maybe you have algorithms that are more accurate for your location and the types of construction that are in that city. So we could consider changing that. Maybe you have a different algorithm for mains water temperature that you would want to use. So we could consider that. And then we would need to define the building that you want to create the draw profile for. Do you want to look at it by number of bedrooms, or do you want to look at it by number of occupants? And if you want to look at it by number of bedrooms, are you okay with California's assumptions for how the number of occupants will change over the year, or do you want to use a different assumption there? If you want to look at number of occupants, we'll need to change the draw profiles to look at specifically number of occupants. And also we want to figure out if you're looking at single family or multifamily. And if you're looking at multifamily, do you want to combine a whole bunch of different dwellings or focus on a single one? If we answer those questions, then we're good to go.
Great. Thanks for that, Peter. So we are running here at the end. So we encourage you to join us for the Zoom portion of this meeting. And so I wanted to remind you all that if you should see a link in this interface, but if you don't, there's a widget at the bottom of the page with like people and chat bubbles, and that should give you the link to the Zoom meeting. For our presenters here, I actually just put it in our team chat. So you all should be able to copy and paste it that way. But yeah, see you all in there soon.
Okay, see you over there.
Thanks.